This lecture will be the last one focusing on the basic elements of Python. Next week we're going to start looking at libraries that allow us to do more interesting things with our data, but first we're going to look at how to access files and to organize data better in our programs with dictionaries. So we're going to start looking at using text files and processing strings. So I'm going to give an example of simulating digestion of DNA with restriction enzymes, and then we're going to look at how to organize data in dictionaries, and I'll give an example from molecular mass. So apologies for all these examples related to chemistry and biochemistry, but it's the easiest for me to find this kind of examples. Also, don't worry if by this stage things seem a bit confusing, these basic elements, because even though we're going to start looking at libraries for useful tools for processing data, we will be always revisiting these same elements. So you have the whole course to practice this and to start getting familiarized with the conditions, loops, functions, using files, and so on. So files basically are sequences of bytes that we store in persistent storage. What you have in memory, in RAM, in your computer disappears when you turn off the computer, but things that you have in hard drives, memory cards, and so on remain there even after power is turned off. So what you have are sequences of numbers, bytes. Each byte has a set of 8 bits, 8 zeros and ones. So basically you have numbers between 0 and 255. These are the combinations that you can do with 8 zeros and ones. And you have long strings of these numbers. These are the files that you have in the computer. So all the files are byte sequences. It doesn't matter if it's an image file, a sound file, a text file, and so on. Those labels that we append are just different ways of interpreting the series of numbers, but all the files have series of numbers. So that's what they are. We can represent easily these bytes in hexadecimal. So hexadecimal uses digits from 0 to 9, and then letters A through F for the other 5 numbers. So basically we have 16 different digits, or the other 6 digits. We have 16 different digits, and so we can represent 4 bits or combinations of 4 zeros, ones with a single hexadecimal digit. This means that we can use 2 digits for representing 1 byte. And this is why hexadecimal is useful for representing this kind of data, because each pair of digits here represents 1 single byte, and they all have the same size. If we were using decimal numbers, sometimes you would have to need 3 digits so to represent all the numbers above 100 and up to 255, so that would be less convenient. But this is just to illustrate that this text here, so this is actually what I write to create these slides. I use a Python script to convert the text into HTML, so I actually practice what I preach here. This is not just telling you how to do things. I actually do them in this way, and this is the text of this. So actually, this slide here, and so if we look at the text file, if we open it with the text editor, we see something like this, where we have lines of text and then line breaks and then spaces and things like that. But if you actually look at the sequence of bytes in the file, you don't have these different lines. You have everything in the same block, like it's represented here. And what indicates to the text editor that you have a line change are these special characters. They are represented here as dots, which in this case it's 0A. This is character 10, or byte number 10, which is a special character. It's interpreted by the words, the text editor, as that special character that indicates a line break. So when it finds that special character there, it will continue in the next line. But there is no actual bidimensional representation of the text inside the file. The file is just a sequential series of bytes, and then the text editor interprets those bytes according to these rules. This is the same for any kind of file. So this, for example, is a WAV file from the audio recording of a lecture, and you also have these different decimal representation would be like this, but you also have the different values from 0 to 255 in all the bytes, and all the bytes in a sequence. So all the files are exactly the same thing, sequences of bytes. It's just the way we then interpret them that makes all the difference in what we see when we have the file. So this is the way files are stored in the hard drive, in your memory cards or hard drive or something like that. But the way we access them in Python is simplified. We don't need to worry about those bytes and so on. So by default, if we want to read a text file or write a text file, we just deal with Python strings, and the interpreter and the operating system takes care of whatever is needed for actually accessing the file. So if you want to read the file, you can use this open object to access the file. So this open function gives you a file object that you can use to access the file. And by default, the mode is R for reading. So for example, if you have this file in the hard drive, so this would be the name of the enzyme, the sequence of DNA it recognizes for cutting, and the sequence of DNA with the indication of where it needs to cut. So this would be the information we have for our enzymes. We can open this file by using the open function from Python and giving the name of the file. So one detail here, this only works if you are working in the same folder as the file. So when you press F5 on Spider, it runs your code in that folder where you have the code, and if you have the file there, then Python can find it. So this in file will now be an object that can access the file, and you can actually use it, for example, as an iterable in a loop, and in a for loop, and it will iterate through all the lines in the file. So if we do this loop, for line in file, print line, we actually see printed out each line of the file in the console, because each pass in this loop, it gets one line from the file and prints it out. When you stop needing the file, you can close it so that other programs can use the file if necessary, and it's not locked for you. This is just to illustrate how the open function works, but actually when you're reading files, the most practical way, assuming that the file can be stored in memory, so if it's a very, very large file, you should not do it this way. You should read one line at a time, otherwise you will occupy all your memory. But if the file is small, which is generally the case of the examples we're going to see, you can use the open function to obtain the object that has access to the file. Use the readlines method from that object immediately. The readlines reads all the lines of the file into a list of strings. So this list, each string in the list is one line in the file. And this will immediately close the file and erase it from memory, so the file object, because you won't have any variable holding the file object. What you get is just the result of reading the file. You store the lines there and you don't worry about the file. The interpreter will take care of closing the file and cleaning the object from memory. So this would be the most useful or used way, most common way of reading a text file. You open the text file and immediately call read lines. You get a list with all the lines as strings, and then you can do whatever you need with that file. Note that this special character that indicates the line change, so this is what actually stores or encodes the line change in the text file, because there are no lines in the file itself. The file is just a sequence of bytes. This character is retained in all these strings. So if we don't want it, we may need to clean it up later. Okay, so other thing we can do is to write a text file. To write a text file, we also use open to get an object that allows us to access the file, but we add this argument w for writing. And then with this object, we can use the write method to write anything we want into the text. But note that you must include this new line, so this \n, the special new line character, if you want to have a line break at that position. So suppose we do this. We open test.txt for writing. This will create this file, or if it doesn't exist, if it exists, it will delete everything inside the file. So open for writing guarantees that you have a file with nothing written in it. And then we can write some text, for example, here, some text. This is written in the file. And then if we write some more text, it will be written after the first block, because this will all just go in sequence into the file. If we want the text editor to represent this text, putting a line break here, we need to actually insert it there with that \n. So if we do this, now we have another line break here and so on. So remember, if you want to format the text in some way into different lines, you can put the \n there. So we can read also and write binary files if we add this b here. So if you want to read and write binary files, you can use these options. But because Python, when dealing with text files, automatically does these conversions of strings into the right format, especially if you have things like encodings for using special characters like special accents and things like that. So this is usually the way we're going to use files with as text files. There are some binary files that we're going to use, but we're not going to use Python at this level for dealing with binary files. We will use files, for example, for images, Excel, and so on, but we're going to use libraries that allow us to access these files. So this is just to mention that you can open, read and write binary files with Python, but this is usually too complicated. If we have standard files like zip files, Excel files, and things like that, we just use a library to with the adequate functions for processing those files. So let's see an example of using these. We have one file called sequences.txt that has the identifier of each sequence, then a colon, and the sequence, the DNA sequence for that sequence. Okay. A series of characters, a string with the symbols for the nucleotides. And we have several sequences there. Then we have this file enzymes that has the name of restriction and restriction enzyme, the sequence of nucleotides that restriction enzyme will recognize in a DNA sequence, and the same recognition site, but marked with the place where the enzyme will cut. So this means that this enzyme echo R1 will find these sequences in the DNA, and it will cut between the G and A here at the beginning. And then we have different enzymes, echo R2 cuts this way, and so on. So this file has one line per enzyme, and this contains the name of the enzyme, the recognition site, and the cutting point there. So the goal is to create for each enzyme a file that has the name of the enzyme, .txt, and then lists each ID of our sequences and the number of fragments obtained if we digest the sequence with that enzyme. So how many times it will be, how many fragments will arise after cutting with the enzyme. And we want to create that for each enzyme in the list. So we want to automate the generation of all these reports. So first, what we need to do is to think about the program. How are we going to implement this? We're going to start by reading the sequences into a list. We can use a list of tuples because each tuple will contain the identifier and the sequence. And so all these pairs we will store into a list. It's important when you're thinking about your program also to think about how you're going to organize the data inside your program, because that has a great role in how everything fits together. Then we're going to do the same with the enzymes. We're going to read them into a list, but in this case the tuples will have three elements: the identifier of the enzyme, or the name of the enzyme, the recognition site, and the cut point. Now we're going to need a function to digest one sequence with one enzyme. So we need to digest all sequences with all the enzymes, but we're not going to start by doing that in a single function because we need all the combinations. So the one easy way of decomposing these problems is to think about what you need to do over and over again, and that is a good candidate for a function. So if we need to do the digestion of all sequences with all the enzymes, we need to do one sequence with one enzyme many different times with many different combinations. So this would be one function: digest one sequence with one enzyme. And then we're going to do that for one enzyme and all the sequences and write that for a file, in a file for that one enzyme. So this could be the other function that's going to do the digestion of all sequences with one enzyme and write the results to a file for that particular enzyme. And then we can create a function that does everything by calling this one here for each of the enzymes. So once we have all of these implemented, it's easy to wrap things together and just loop through all the enzymes and write everything to the different files. Okay, so this is the plan for the program, and you should, before starting to program anything, think a bit about how to organize your program. And now we can actually write the skeleton for the program by writing the signatures, the headers of each function. So one thing I suggest is that you actually start your source code with Spider and then simply write the definition line of each function, indicating the name and whatever parameters you need, and then writing the documentation or a very brief description of what the function does. This is important, especially in the beginning, because it allows you to check if things will match, will fit together. So this first function receives the name of the sequence file and returns all the tuples of the identifier and sequence. This does the same thing for the enzyme, so the name of the enzyme file, and it returns all the enzymes in the file, the identifier, the recognition site, and the cutting point. And then we have this function that will return the fragments obtained by cutting this sequence with an enzyme. And we can specify how the enzyme cuts by providing the recognition site and the cutting point. And this will tell where in the sequence the cut will occur. Then we're going to create the report for that enzyme, and we can create the report by adding the name of the report file, all the sequences that we need for that report, and the information necessary to compute how this enzyme will cut each of these sequences. So as you write this, you can think if each function has the necessary information and if each function can call the previous one. For example, to create a report, we need to loop through all the sequences and call this function to compute the fragments for that particular digestion. So we need to see if we have the information necessary to do that and to check if things will fit together at the end. And then we put everything together. We have the sequence file, the enzymes file, and we read the sequences, read the enzymes, loop through the enzymes, and create the report for the enzymes. So we think about the program, we outline it here by writing the headers for each function. And now the big advantage of doing this is that we can now focus on implementing and testing each individual function without worrying about the big picture. We can just focus on each small individual problem now. So let's start with the first one, read the sequences. We receive the name of the file that has all the sequences, and we need to produce a list with identifier and DNA sequence for each of those lines. So we start with the empty list here, and now we're going to open the file and read all the lines in the file. So now we have all those lines that have this data, ID, colon, and the DNA sequence, and we have them all in a list of strings. So we can now loop through all these strings with a for loop. So for each SL, this is the string in the list, or the sequence line, if you want, in all these lines. We can now split this using the colon, this separator, and break it down into two parts: the identifier of the sequence and the sequence itself. And now we can append this to the list that we're building. Now there's one small trick here, because if we read this from the file, at the end of each sequence, we're going to have this new line character that tells the editor to change to the new line. And this will be included in the strings when we read them from the file. So one useful way, or one practical way of doing this, is to use the strip method from the string. Strip is very useful because when you have a string with anything that is white space on the extremities, whether it's on the beginning or the end, if you use strip, it will delete all of those elements. So white space is everything that is not visible. It can be an actual space, it can be a line change, a line break, it can be a tab character or something like that. So strip will not change inside the string, but all the white space at the extremities will be eliminated. So we will append to our list of sequences a tuple with the identifier and the sequence cleaned out of all these special characters for the line changes. And now we return this list. So before moving on to the next function, we test this function, and we do this. We read the sequences file, we store the list in this variable, and now we check what this variable has. So it has all these tuples. I cut away the strings because they're too long, but we can actually check and compare to the file if we are getting the right identifiers and the correct sequences, and if everything matches up. So it's always a good idea to test your functions before moving on to do these unit tests, because once you start fitting everything together, it becomes harder to spot mistakes. So now for reading the enzymes, it's basically the same thing. The difference is that the enzyme data is in a slightly different format. So we have, on each line, we have 3 elements separated by a semicolon. So what we do here in this case is, instead of splitting by the colon into 2 fragments, in the enzymes we are splitting by the semicolon into 3 different fragments: the identifier of the list, the recognition site, and the cutting point. So remember that split produces a list of substrings by deleting that separator. Since this list must always have 3 elements, because we always have 2 semicolons in these rows, in these lines, we can unpack it into these 3 variables. And now we do the same thing. We append to our list of enzymes the tuple with the 3 elements, which is the enzyme identifier here, the recognition site here, and the cutting point from which we're going to strip the new line character. Otherwise, we would get something like this, and this is not what we want. We want just the actual text and not those white space characters. And now we return the enzymes and we check to see if everything matches. So these are the two functions that read the files. Now we need to create the function to actually do the digestion. So this one is easy. We're going to use this trick of marking the sequence with the cutting point by using the replace method. So to recall this, we are going to find all instances of the recognition site in the sequence and replace it by the string that has the cutting point marked there with the minus sign. So now it's easy to cut at that region by splitting on the minus character. So this is a very easy function to write. We just need these 2 lines of code to do the replace and then cut. And we can actually test it with some artificial strings to make sure that everything is working okay. So this would be our hypothetical sequence, the recognition site of a hypothetical enzyme, and where it cuts. So it cuts between the T's, and now we can see that the function is working and it's cutting wherever it finds 2 T's precisely between them. Okay, so now we need to use this function to create a report with all the numbers of fragments we have when we cut all the sequences with one enzyme. So this is the create report function. The name of the file is the file we're going to create. So we have this out file here, this object, which is obtained by opening a file with that name for writing. If the file doesn't exist, it will be created. If it exists, then it will be every content will be erased and the file will start at 0. And now for each sequence that we have here, so this sequence record is a tuple, these tuples that we have here with the identifier and the actual sequence. For each of these, we can unpack it into sequence ID and the sequence. We can actually do also this in one line over there, but this may make it easier to understand at this stage. So we unpack this tuple into 2 variables, and now we compute the fragments obtained by cutting this sequence here using the recognition site and the cutting point of the enzyme we received in our parameters. So we're going to loop through all the sequences and cut it with this enzyme. And this will be the list of fragments that we obtain after digestion. It will be something like this. And now we're going to write into our file the identifier of the sequence, a tab character, and then the number of fragments we have. So one way of doing this, we'll see different ways of formatting strings, but this is one easy way of doing it, is to use a template string in which you indicate with the curly brackets where each argument of the format method will be placed. So this will be argument 0, this will be argument 1, it's in the order here, and then we use the format method and give the arguments that we want placed there. So at the beginning of the string, format will place the identifier, and after the tab it will place the length of the fragments list. In other words, the number of fragments we obtained. So then at the end of the loop, once we go through all the sequences, we just close the file. Note that we don't need a return here because this function doesn't actually return anything. It just creates the file. So we don't have a return statement, and once the function ends, it returns with a none value. And now we can check to see if this works. So we can create some artificial sequences, S1, S2, S3, with these sequences here. We create the report on this test file using these sequences and this information for cutting. So every time the enzyme finds a TT, it will cut between the 2 T's. And now we can check what the file contains. So you can either open it with a text editor to look at the file, or you can just print the result of this opening the file and reading everything. So reads everything in the file as a string, we print it out, and this is the content of the file. So for string 1 we obtain 2 fragments, it cut here. For string 2 we have 3 fragments, it cuts in two places, and for string 3 also 3 fragments. So this is one quick way of checking if the function worked. Okay, so now we put everything together. We create this final function that receives the sequence file and the enzyme file. It reads all the sequences, it reads all the enzymes, and now it's going to loop through all the enzymes, and for each enzyme it's going to unpack the tuple we have here. So remember that when we read the enzymes, we have a list of tuples with these 3 elements: the identifier or the name, the recognition site, and the cutting point. And now what we're going to do here is we're going to unpack this into these 3 variables: the identifier, the recognition site, and the cut point. And we're going to create a report into a file that has the same name as the enzyme plus a txt extension. It's going to have a report with all the sequences that we read here, and using the recognition site and the cutting point of this particular enzyme. So for each enzyme we have different results depending on what they recognize and where they cut. So we can test this by running the function and then looking at each individual file and see if everything is working fine. Okay, one important thing is that you can access files in any place in your drive, but if you just put the file name, Python will assume that you have the file in the same folder where you are currently working. So when you do F5 in Spider, it will run your code, but also set the working directory, the folder where you're working. So if you do this and you have the files in the same folder, then this works perfectly. Python can find your file just from the file name. If you have your files in other folders, you can use relative path. For example, we need to go back up one folder, then into the data folder, and then my file. You can do this, or you can use absolute path, either in Windows or in Linux, as you want, if you have the file in one specific case. But often it's more practical, especially in exercises, that you have the file either in the same folder or in a subfolder. For example, like this. If you have a data folder with the file, you could do something like this if you are working on the folder where the data folder exists. One important thing is that the backslash, so this character here, would be a special character, would be an escape character for putting those special characters like the line change and the tabulator and so on. If you use this on Windows, you need to put 2 of them so that Python understands that you want to put an actual backslash and are not just indicating that you want to put a special character. However, Python also understands this more sane notation of using the / even in Windows. So even if you are working in Windows, you can use the / as in Linux or Mac OS. So it works the same there. So my recommendation is to always use the /, but if you want to use the backslash, you need to put 2 of them, something like this. Okay, so now let's see dictionaries. We saw how to read data from the files, but now we can find a better way of organizing data in memory. So we saw here that when we wanted to store the sequence for each, the identifier and the sequence, or the enzyme identifier and the data for the enzyme identifier and so on, we put everything in tuples. So we have a list and everything is in the same order. First comes the identifier, then the recognition site, and so forth. This can lead to mistakes sometimes and it takes longer to search for specific items than if we can organize the data in a way where we have keys associated to values. So we can add names to different fields, we can organize things better. And dictionaries allow us to do that. So a dictionary in Python is a set, not necessarily an ordered set. So although in the more recent versions they retain the order, but the idea is that you have a set of keys associated with values. So this is something like a dictionary where you have the word and the meaning of the word, or a phone directory where you have a name and a phone name number, and so on. So every time you need to pair together some key with some value, then you can use a dictionary. The key must be an immutable object. It cannot be a list, for example, but it can be a tuple or a string or a number, something like that, because those are immutable in Python. The value can be any object, including other dictionaries. You can create trees of dictionaries under dictionaries if you want. Indexing is done via the key. So for example, we can define this capitals dictionary by indicating for each capital what is the corresponding country. And the syntax here is we use curly brackets at the beginning and the end, and we pair the key and value together using the colon character. And we separate the entries with the comma. So Paris is a key that has associated the value France. Lisbon is another key that has Portugal associated to it. London another key with United Kingdom. So now we can ask for example, capital is the Paris of which country? We can ask in our capitals dictionary the information for Paris, and we get France as the response, the result. So with this, we can easily assign this association of values to keys. We can add or replace entries into the dictionary. For example, if we say that the capitals Madrid is equal to Spain, this adds a new entry into the dictionary which has Madrid corresponding to Spain. Okay. So this makes it easy to organize data whenever you need to pair things together. So for example, for our restriction enzymes, we could create a dictionary for all the enzymes, and then for each identifier, which is one key in our dictionary, we would associate another dictionary with one entry called with the key recon for the recognition site, and the other for the cutting point. So in this case, we could obtain this dictionary of enzymes that has for each identifier another dictionary with the data that we want. And if we want to find, for example, the cutting point of ALU1, we can say from the enzymes dictionary, get me the entry for ALU1, and then for that one, we get the entry for the cutting point. And this will give us the information that we have there. And so forth, we can do this for any enzyme and for any attribute there. So this makes it easier to avoid mistakes because we can specify in a more readable way what we want at each stage. So let's see an example of using this to compute molecular mass. We want to create a function that does something like this. We give it a chemical formula. For example, calcium carbonate, we have Ca for calcium, C for carbon, and 3 oxygen. And this returns the molecular mass. So it adds up the mass of all those atoms. The same thing for aspirin, for acetyl salicylic acid, or for this salt with platinum and chloride and so forth. So we want to create a function that does this. And what we need here is to know the atomic mass of each element. We need to think about the algorithm for decomposing the chemical formula and create the outline of our program. So for the atomic mass, we can look up in the internet. I copied these values, and basically I have this file, periodic table, that has the atomic number, the symbol for the element, the name of the element, and the atomic mass, the average of the isotopes for this element. So now we're going to think what we're going to do. We're going to read this file into a dictionary where we have the mass for each element. And then from the chemical formula, we're going to create a list with the chemical symbol, so the element, and the number for each element there. And to do this, we now have to think about how to break down this sub-problem into smaller problems. One thing we need to do is find uppercase letters, because in this convention, uppercase is always the beginning of the element name if it has 2 characters, or it's just the whole element name if it only has 1 letter. So we can create a function to find the next uppercase, and we go iterating through the formula, going jumping on all the uppercase letters and removing each part, each bit for each element. So we're going to slice this into the different atoms that we have here, the elements, and also keep how many atoms we have of this element in each fragment of our chemical formula. And then we're going to interpret this, and to obtain the mass, we can simply add up the mass of all the elements multiplied by how many atoms we have in each fragment. So this, we can look up the mass of each element in this dictionary and then just add everything up. So let's create the outline of the program. We need a function to read the dictionary of atomic masses. We need a function to help us find the next uppercase letter when we are moving through the chemical formula. Then we need to convert a fragment of the chemical formula, something like this, into a more easily interpretable structure. For example, a dictionary that tells me that O3 is the atom of element O with 3 times that atom, so I can easily do the operations. So this convert will create a dictionary that has the element and the number of times that atom appears. Then we write this function that receives a formula and decomposes the formula into a list of these fragments. So a list of these dictionaries that say, here is a calcium atom, here are 3 oxygens, and things like that. Finally, we just add up everything. So this molecular mass function will just call the decompose function and then loop through all the fragments and add up all the masses. So after we plan the program and we write the outline, we know the different functions we're going to write, we can start writing each individual function without worrying about the rest. So to read that file into the dictionaries, we're going to read all the lines in the file. So remember, the file is like this. So the first line has the headers, the second line has hydrogen, helium, and so forth. We're going to skip the first line, so we're going to slice the list of lines by skipping the first one till the end, because the first line has the headers, we don't care about that. We're going to split through the tab character, because this is how these are separated, the different attributes there. And we're going to insert into our dictionary as a key the second cell in this line, because this is the one that contains the symbol of the element, and the associated value will be the last cell, the 4th cell, which is the one that contains the atomic mass. But since this is a string, we need to convert it into an actual number. So we convert that into a number and we store it in the dictionary. And now we can test what happens when we read this periodic table file. We get a dictionary with the different elements and the associated atomic mass. So we tested our function. We now have a dictionary with the masses that we can use to add up all the masses in the molecule. Now we're going to find from one chemical formula, starting at some particular position, we want to know where is the next uppercase character, uppercase letter. So we can do that by using the isUpper method. The isUpper method of a string returns true if that string is all uppercase. So we're going to loop through the formula here, but starting at the index point, because we don't want to always start at 0. If we already found one uppercase character, we want to skip that and find the next one. So we're going to start at index. We're going to all the way to the end of the formula if necessary. But if the character at that position, IX, is an uppercase character, we're going to exit the function immediately and return ix. So if this function is starting at character index 2, for example, which is this C, it's going to start at this character. This is an uppercase character, so it returns immediately, and it returns 2. If it starts before, for example, at A, then it's going to skip this part, it doesn't return, and it's going to try the next position, which is 2, sorry, and it's the uppercase C there, and then it returns. If it doesn't find any uppercase character, it will reach the end of the loop, it will reach the end of the formula, and not finding any uppercase character, so now we return the length of the formula. This means that we couldn't find any more uppercase characters. So now we test the function to see if it can find the right character, and now we're going to use it to decompose our formula into these different fragments. So we need to take these parts of the formula, for example CA or C or O3, and transform that into something that is more useful for us, which is a dictionary like this. It tells us how many times the atom occurs and what is the symbol of the atom. So to do this, we're going to start with these strings empty, the symbol and the number, and we're going to look through all the characters in this string, the fragment, and check if this is a digit. If it's a number, we're going to add the digit to the number here. So is digit is true if you find something that is a digit. Otherwise, we're going to check if it's an alphabetic character. So if it's a letter, it can be uppercase or lowercase. If that is what happens, then we're going to add it to the symbol. So you see that in this loop, we have an if and an elif, but we don't have an else. So if by looping through all the characters in the fragment, if we find a digit, we add it here to the number. If we find a letter, we add it to the symbol. If we find something else like parentheses or spaces or things like that, then we ignore it because there is no other branch here. So this just extracts into the symbol all the letters and into the number all the digits. Now we check if the number is empty. For example, in calcium, in this case, there are no digits in this fragment. So the number is an empty string. That means there is only one atom. Otherwise, else, if we have some number here, for example, in this case, then the number is the integer of this string. Because we stored these characters as a string, but now we need to convert it into an actual number. So this will return the dictionary that has one symbol entry with the symbol of the element and one number entry with how many times that atom occurs. So if we convert O3, we get a dictionary with number 3 symbol O. If we convert CA, we get a dictionary number 1 symbol CA. So this is very useful to understand what atoms we have and how many times, what elements we have and how many atoms of each element there are. So now we can decompose the formula. We start with an empty list of all the different atoms in the formula, and we find the first uppercase character. So this allows us to skip any characters that may appear in the formula before the first uppercase. So this will be the current one, will be this C of CA at the beginning. Now, if the current uppercase character is not outside the formula, remember that when we don't find any more here, we return the length of the formula. So this is outside of the formula. So while the current character is less than the length of the formula, we're going to find the next one, the next element, by going to find the next uppercase character in the formula, starting from the next position of the current one. So if we start at this C of carbon, we're going to find of calcium, sorry, we're going to find the carbon by starting from the A and then going forwards until we find the uppercase character there. So this is the current one. The current one is the C from Ca, and the next element will be the C from carbon. So now we're going to append to our atoms list the dictionary found by converting our formula from the current element up to the next one. So we get all this Ca and not the C, the C that comes afterwards. And we're going to convert this little fragment into these dictionaries and append it to our list. And now we're going to skip ahead to the next element. So the current one will now be the next one. And we're going to keep doing this until we reach the end of the formula. So this, if we put something like this, CaCO3, we get this list of dictionaries. We have one atom of element Ca, we have one atom of element C, and 3 atoms of element O. If we do this one, K, PT, Cl, and so forth, note that the parentheses are ignored. We have one atom of symbol K, one atom of symbol PT, 3 of Cl, and so on. Of course, this doesn't work if we have something on some number on the parentheses or something more complex like that. But for simple formulas that don't have those kinds of complications, this works. So now we can bring everything together with the final function. We receive a formula. We read the dictionary of masses from the file. So remember that this is a dictionary that tells us for each element what is the atomic mass. Now we call the decompose function on the formula, and we obtain a list of dictionaries with the entries for the number and the chemical element. And now we just start with the mass at 0, and we add the mass for all the different elements. So we get from the dictionary the element of that symbol, and we multiply that by the number of times the element occurs. So for example, in this case, the mass for calcium will be multiplied by 1, the mass for oxygen would be multiplied by 3, and so on. So we just add everything together and return the mass. And this is how then the function works. We can test with different formula and check if the mass is correct. So one extra problem, suppose we have now a file with different chemical compounds, and we want to create a table with all the chemical formula and the corresponding masses. This would be very easy to do. We just add another function that reads the file with all the formulas, opens the report file for writing, and now for each formula it just calls the molecular mass and writes to the file the mass, the formula, and the mass. Now here I can show you here how you can actually format the numbers. So if you look at these floating point numbers, they have many decimal places. But if you want to format them, for example, for 2 decimal places, you can use that option here. So we are using format to put there the second argument, which is the mass, and we want it to have this format. So you put a colon, dot 2f. This is a floating point number with 2 decimal places. This is not something that you should memorize, but you can always look up the documentation and see this kind of formatting. So you can do this with format. You can also use the f strings. So only f strings are tricky in this case because you cannot add these special characters on f strings, but you have different ways of doing this kind of formatting. It's a good idea to know that they exist. You don't need to memorize how they work because it's easy to use Google and see how to format strings in Python. But if you know that you can do this, you're already halfway to getting it done. The rest is easy. So this would be running our function. Mass table, we read from the formulas text, from the formulas.txt file, which is this one, and we write this table with the masses. So the idea here, remember, is that if we decompose our problems and we have these different functions, then it's easy to reuse them and to adapt them to new kinds of problems. So just quickly passing through some kinds of errors that may occur when you're writing code. So the best one is the syntax error. This occurs when you do something that the interpreter cannot understand. For example, this should be like this. for the exponential. If you write it with a space, you'll get an invalid syntax because the interpreter doesn't understand this. Or this 5.3.2, something like this. This is a good kind of error because the interpreter tells you exactly where it occurs, except perhaps when you're missing parentheses. If you forget to close parentheses, you may get the error on the next line and be a bit confused by what the error is, but you get the error exactly or near the place where it occurred. And also Spider analyzes the code as you type, so you'll get some warnings of errors in the editor even before trying to run your code. Execution errors are a bit trickier because the interpreter understands what you want. For example, y equals to z raised to the power of 2, but cannot do it. For example, in this case, if z is not defined, it's not possible to compute the square of z. In this case, for example, we are trying to divide by 0, and this will result in an exception. So all these errors in the execution are exceptions that the interpreter raises, and they tell you that something went wrong and your code stopped. This can be a bit harder to fix because the error here may be because you mistook the name of this variable and it was something else, or it may be because this variable should have been defined earlier in the code and it wasn't. So it's not guaranteed that the error occurred where the program stopped. It could be due to some other problem. A logical error is worse than the other two because a logical error occurs when the program runs. There are no errors. Python doesn't tell you anything is wrong, but the result is wrong. Because Python doesn't know what the result should be. It only does what you tell it to do. And if the result is wrong, you need to figure out what went wrong. For example, suppose we have this function to compute pH. We compute the pH of some solution and we get a negative value. Now, there was no error that Python raised because everything worked fine, but we forgot the negative sign on the logarithm. And so now we have to go look at what's wrong with the function. And this may be quite some work if you have lots of functions together that you didn't test properly. So this is one main reason for testing your functions, to see if they run and to see if they give you the correct value. Otherwise, it may become very difficult to find errors because if you did not test the solve quadratic function, for example, it could be an error there or it could be an error somewhere else, and that would make it very hard to fix the errors. Okay. Then there is another error that usually is not very bothersome, but you need to keep it in mind, that floating point numbers are represented with 8 bytes, so 64 bits. You have the significant part here, which limits the number of significant digits. Then you have an exponent of 2 and a sign for your value. So this means that you have a limited precision on the numbers. And if you do something like this, for example, you take the square root of 2 and then you raise it to the power of 2. So the square of the square root of 2, and this is not 2. Is 2.0000, lots of zeros and a 4 at the end. This is because square root of 2 is irrational. You cannot represent it with a finite number of digits, so it gets rounded off when Python computes this. And then when you square it, you see the rounding error occurring there in the square again. So you can have an idea of the precision here. You have if you import NumPy, that numerical Python library, you can get information on the floating point numbers. These are the number of bits that are used. This EPS is the smallest value that you can add to 1 and still make a difference. For example, if you have 1 minus EPS, 1 plus EPS minus 1, you still have some value remaining, the EPS. But if you do, for example, 1 plus half of EPS minus 1, you get 0, because when you try to add half of EPS into 1, this gets rounded off because it's outside the precision of the representation for 1. So now it's as if it didn't exist. So you can see what is the smallest value that you can store with full precision, the one closest to 0. So it's 10 raised to minus 308, around that. And then the smallest and the largest numbers that you can represent. So about to the power of 308. So this is usually enough for most operations. If you have something very tricky where you need to compare floating point values and you are dealing with irrationals and things like that, remember that you need to give some margin of error in that case, because you'll have rounding off errors. Okay, so to sum up for today, before we jump into the Zoom session, we saw for this part how to access files. You use the open function. This gives you an object that allows access to the file, and you can read or write the files depending on the argument in open. If you're writing to the file and using the file object several times, remember to use close at the end. If you don't close the file, what happens when you're writing is that Python is sending the instructions for writing to the file to the operating system, and usually the operating system stores everything in memory and then writes to the file when there is low use of the system or something like that, to optimize file access. If you don't close the file, then it may happen that things don't get written there and you don't have anything in the file. Also, closing the file lets the operating system know that you're no longer using the file. So if you're reading with read lines, Python will close the file automatically, but usually when you're writing and using the file object repeatedly, you should close the file, otherwise you may have some errors there. We also saw dictionaries. You can see these chapters 10 and 14 of Thinking Python about these subjects, and I will go now to the Zoom session if you have any questions. Okay. So just one more thing, you have this mandatory exercise for this week about global warming on chapter 4, but don't worry if this is a bit too confusing, because these first 2 weeks are a bit intense. So follow the lecture examples, whatever lecture you're comfortable with, so you can go back to the previous ones and go at your own pace. You have these tutorials also on on chapter 3 and chapter 4, where you have all the examples with the code, either from the lecture or from the tutorial, so you can follow things step by step if you need, and you have the other exercises for practice. Okay, so I'll go to the Zoom session now.